Hello, my name is Brooke Feeling, and my presentation is entitled Isolated Hot Poor: Assessing the Relationship Between Urban Heat Islands, Vulnerability, and Emergency Services Access in the Twin Cities metro area. My basic outline is first I'll talk about the purpose, then I'll move on to the question, then some background on urban heat island, heat stroke and access, vulnerability. Then I'll talk about my study area, then heat islands, access and vulnerability maps, and then my final map, then a scenario, conclusion, future research, and my data. The purpose of the study was that by working with our partners, Catholic Charities in Ramsey County, we aim to address the issue of heat stroke in the 7-county metro area of the Twin Cities by using GIS to determine areas that are hot, with low access to emergency services, and a sensitive, vulnerable population. Our research question was, using ArcGIS, can we identify areas in the 7-county metro area of the Twin Cities where there's a sensitive, vulnerable population exposed to high temperatures with low access to emergency services? Now I will offer a brief background on urban heat islands, their effects, heat stroke, and vulnerability related to them. In short, an urban heat island is a metropolitan area that is significantly warmer than its surrounding rural areas due to a variety of factors. So basically, I like to think of it kind of as this little bubble around urban areas where temperatures are higher than their surrounding non-urban areas. So you may be wondering, why are they hotter? Well, in short, this is due to the changed landscape in urban areas, which leads to increased temperature. As urban areas develop, changes occur in their landscape. Buildings, roads, and other infrastructure replace open land and vegetation. Surfaces that were once permeable and moist become impermeable and dry. These changes cause urban regions to become warmer than their rural surroundings, forming an island of higher temperatures in the landscape. The first image on the left shows a further depiction of how temperatures can vary between a downtown or urban area compared to suburban and rural areas. You can see it's just a few degrees difference, but that plays a huge role in a variety of areas I will touch on in a bit. The second illustration depicts what I spoke on previously, how in urban areas, surfaces that were once permeable and moist become impermeable and dry. You can see here that evapotranspiration, which is a process of transferring moisture from the earth to the atmosphere by evaporation of water and transpiration from plants, which in turn lowers temperature as this cool, moist air is released. You can see how this decreases in urban areas because of the lack of vegetation there. There are 4 main effects of urban heat islands. There's increased energy demand, air pollution and greenhouse gas emissions, heat-related illness and mortality, and impairment of water quality. So for energy demand, this means higher temperatures in summer, and that increases the energy demand for cooling. So one study estimates that the heat island effect is responsible for 5 to 10% of peak electricity demand for cooling buildings and cities. In terms of air pollution and greenhouse gas emissions, this is building off the previous point in that increasing energy demand generally results in greater emissions of air pollutants and greenhouse gas emissions. For heat-related illness and mortality, warmer temperatures can contribute to discomfort, respiratory difficulties, heat cramps and exhaustion, heat stroke, and heat-related mortality. For impairment of water quality, because the pavement absorbs so much heat and is hotter, the stormwater passing over it is heated. In fact, pavements that are 100 degrees Fahrenheit can elevate initial rainwater temperature from roughly about 70 degrees Fahrenheit to over 95 degrees Fahrenheit. And this increased water temperature affects the metabolism and reproduction of many aquatic species. Now I just wanted to highlight the health effects associated with urban heat islands. Some health effects are general discomfort, respiratory difficulties, heat cramps and exhaustion, non-fatal heat stroke, and heat-related mortality. In fact, the CDC estimates that between 1979 and 2003, excessive heat exposure contributed to more than 8,000 premature deaths in the United States. So you can see it's a huge issue with health effects. Next, I want to use this image because this image ties everything together nicely, showing that exposures, both direct and indirect, environmental conditions, social conditions, and health system conditions all contribute to the health of a population. So now, knowing this basic information of urban heat islands and their associated impacts on a variety of things, we were wondering, so can we identify areas in the 7-county metro area of the Twin Cities where there are urban heat islands, where there are sensitive populations being exposed to this heat, and then knowing what we know about health effects associated with this heat, we wanted to know where people can't easily access emergency services, so that we know where problem areas are where people are essentially isolated, hot, and poor. In doing research, we came upon this great diagram tying all the pieces of that contributed to vulnerability together. These were exposure, so exposure to the heat, sensitivity, so if they're exposed, are they going to be sensitive to that exposure? And exposure and sensitivity brought about the potential impact on the population. And then there was adaptive capacity. So this had to do with the population's ability to adapt and react to the exposure through health services, etc. And factoring in adaptive capacity to the potential impact, we could then identify if a population was vulnerable. So now came the point to develop a model expressing this. What we did in our study was take 3 models: urban heat island, which related to exposure from our diagram, a vulnerability model, which related to the sensitivity piece, and then access to emergency services, which related to the adaptive capacity piece, to essentially show areas where people are isolated, hot, and poor. Basically, this overall vulnerability that we could then try and later tackle and put efforts towards so that these people are not as vulnerable. So now we're wondering, who is vulnerable? So we started off with exposure, and now I'll break down our 3 models for you, starting with exposure. Some factors we took into account for exposure were biomass, lakes, and impervious surfaces. So more biomass and lakes both had a cooling effect on temperature, while impervious surfaces contributed to higher temperatures. Here are 3 maps showing the distribution of the biomass, lakes, and impervious surfaces or pavement in the study area. So you can see how in the Twin Cities area there's an obvious concentration of pavement, while at the same time a lot less biomass and few lakes, which is contributing to the urban heat island effect. Now, using the exposure idea and our data on biomass, lakes, and impervious surfaces, we created an urban heat island model. This is a model showing how all this contributed to an urban heat island. So essentially places with low biomass, far from lakes, and with a lot of impervious surfaces were the hotter areas. And you can see this here. The red areas are the areas that are the hottest with the high temperatures we are really concerned about. Next, we looked at sensitivity. Some factors that we thought affected sensitivity were low education, low income, elderly, so they're more likely to be sensitive to the heat if they're older, living alone, so you're more isolated that way, rent cost burden, and colored people. These factors and sensitivity as a whole contributed to our vulnerability or sensitivity model. This model shows how we took into account all the factors I talked about before that we thought made up a sensitive population to display places that are vulnerable and sensitive. So you can see here we have poverty rates, percent over 65, percent white non-Hispanic, etc. And here's the map the model gave us. The purple areas are areas with a sensitive population, so perhaps low income, rent cost burden, low education, etc. The green areas are areas with low sensitivity. Next, we looked at adaptive capacity. Adaptive capacity is, it refers to behavioral, institutional, and technological responses and adjustments to lessen the potential impact. Another way of thinking of this is adaptive capacity is the evaluation of a system's ability to cope with the hazards resulting from the heat, which may be measured by access to financial resources, so like federal aid programs, health infrastructure, so like hospitals or ambulatory services, or access to technology like air conditioning. And in our study, we focused on the institutional responses in the terms of health infrastructure and access to emergency services, such as hospitals and fire departments. Overall, we thought that more access to emergency services meant greater adaptive capacity and therefore a less vulnerable population because of that. Another consideration we had with this model is a tool called friction of distance. This is a measure of how absolute distance affects the interaction between two places. It takes into consideration that distance requires some amount of effort, energy, money, or resources to overcome. Therefore, because of this, interactions take place more often over shorter and less costly distances. So for instance, if there's a huge lake between you and the nearest hospital, it's a lot harder to get to that hospital because you have to go around the lake, versus if there were a paved road that went directly to the hospital. So areas with less effort required to overcome had a low friction of distance and vice versa. So as I said, we used the concept of adaptive capacity and friction of distance to then develop our model for access to emergency services. And here is our model. You can see that we took into account locations of fire departments and hospitals to determine emergency services locations, and then looked at friction of distance to come up with the cost distance to emergency services. So basically, the relative ease of access to emergency services. And here is the resulting map. Areas that are blue have the least accessibility, and areas that are yellow have the most. So areas where there's a lot more yellow are generally along major highways and paved roads, things like that. So now this brings us to our final model. For our final model, we put all three of those smaller models together. So our urban heat island model showing exposure to the heat, plus our vulnerability or sensitivity model, and our access to emergency services model showing adaptive capacity of a population to find areas where people are overall isolated, hot, and poor. So this overall vulnerability. So this is our resulting map. Areas in red are the most isolated, hot, and poor. In blue are the least. The white areas are the uninhabited areas, which was important to take into consideration here because we wanted to locate where people are actually living. We didn't want to have areas saying that they're isolated, hot, and poor, but really it's just a factory or a business. Now something really cool we can do with this model is change it depending on what your specific definition of vulnerability is. So maybe for you it's elderly and poor people, or maybe it's people with low education who are of color. Whichever it is, this model can be adjusted to show that specific population so you can then target it based on your needs and wants. So for example, for my scenario, I chose percent rent burden over 50%, percent over 65 over 50%, and percent English less than 50%. And this was the resulting model. You can see there how it's factored in. And here's my vulnerability map resulting from that scenario formula. So that little red area there you can see right below Minneapolis is the area that it identified as being rent burden over 50%, over 65 over 50%, and percent English speaking less than 50%. Now that one was a little far back, so it's hard to see. So I zoomed in here now, and you can definitely see that red area highlighted out there on that map, and you can see the nice streets, so you can see exactly where this population of people are. So now using Google Maps, I actually found this highlighted spot. So this here is Cedar Avenue and 7th Street in Minneapolis, Minnesota. So you can see all the impervious surfaces here, the highways, and the definite lack of biomass, the lack of lakes, as well as this building here to the left of the pin drop, most likely being an elderly home. So you can see our model is very useful and very flexible as well. In conclusion, in our studies, we found that there are higher temperatures in urban areas, there are sensitive populations within the study area, there's a high cost distance to emergency services contributed to the vulnerability of a population, and then overall, there are areas that are isolated with high temperature and a poor population in our study area. So for future research, how can we go further with this? Well, we thought depending on your definition of vulnerable, this could change the area found. So this is the scenario formula I talked about before. Also, we could take into account other factors of adaptive capacity, in addition to emergency services. So things such as access to federal aid programs and air conditioning, so not just hospitals and fire departments. Another thing we could do is reproduce the study in a different area. Thank you for taking the time to listen to my presentation. Have a great day.